This is Calculus 12, Chapter 7.4. We're going to be looking at how to calculate lengths of curves. This is also known as arc length. We can use secant lines to estimate the length of this curve. If we look at this secant, we can see that we have delta y over delta x. We're going to want to calculate the hypotenuse of this triangle. And we can do this by dividing both by delta x. And for this side length, we get 1. And here we have delta y over delta x. And that's just the slope. Okay, so the formula is the length is the integral from a to b, square root 1 plus the derivative squared plus 1 integrate with respect to x. This is the way we actually do it. But what we're doing is we're thinking about it this way. A to b 1 plus delta y delta x squared dx. Okay, so this is the way we think about it, this diagram, and this is what we're doing. Now, unfortunately, the square root makes integration difficult or impossible to do analytically. So it's usually solved numerically. Let's look at an example. Find the arc length of y equals x squared from 0 to 1. So this is our a and b. We look at y equals x squared. Differentiate. Okay, so our arc length goes from 0 to 1. Square root 1 plus 2x squared. And this is where most students make an error. They forget to square this. So now we have 0 to 1, square root 1 plus 4x squared dx. And we can plug this in on our calculator. Okay, make sure you're plugging this in. We're not plugging in this. We're not plugging in the derivative. We're plugging in the formula for arc length. Square root 1 plus 4x squared. And window, that's probably good enough. And then we're calculating the integral from 0 to 1. And we get 1.479. And you should use units as your units. Okay, let's look at a much more difficult problem. Finding the arc length of y equals ln secant x from 0 to pi over 4. And the reason why this one is more difficult is this one can be done analytically. And I've already done the derivative here, but let's go through it. Okay, so to find the derivative of this is a composition, so we need to use the chain rule. So y prime equals 1 over secant x. The derivative of ln is 1 over u. And we need to take the derivative of secant x. And that's secant x, tan x. We now cancel these out, and we have tan x. So, if you recognize this identity, you can jump straight to this identity. Otherwise, we'll break this down. Okay, we use the basic identity. We need a common denominator, cos squared x. And then we can simplify this with a 1. That's our Pythagorean identity. And now we can take the square root of this because it's a perfect square. And the identity for this is secant x. This is a particularly difficult integral because there's no obvious way to substitute this. Because if we let u be cos, the derivative of sine, there's no sine to substitute here. The only way to integrate this is using tricks. And that trick is to multiply by 1. So secant x plus tan x is our 1. This is not obvious. And what we want to do is expand this. So secant x times secant x, secant squared x, secant x times tan x, all over secant x tan x. We need to find a u and the du. So we have to substitute. If we try to make this u, the derivative is actually going to be more complicated because we got to use the product rule here, and we're not going to substitute this out. If we take the derivative here, it looks like this might be the derivative, and that way we can substitute that out. So let's try that. Secant x plus tan x. Derivative of secant x is secant x tan x. And the derivative of tan x is secant squared x dx. So now we see that we can substitute this line out. This is just reversed. That's okay. Now we want to switch to an indefinite integral because we don't want to change the limits of integration. So we have 1 over u du, and we have ln u plus c, absolute value. And now we can substitute back ln secant x plus tan x. And we can put our limits of integration back in, 0 to pi over 4. Now it's just a matter of substituting that in. We have ln and secant pi over 4 plus tan pi over 4 minus ln secant 0 plus tan 0 Okay, this is cos of pi over 4 is 1 over root 2, so we just have root 2. And tangent of pi over 4 is 1. 1 over cos 0. Cos 0 is 1, so 1 over 1 is 1. And tangent of 0 is just 0. So we have ln root 2 plus 1. Ln of 1 is 0. And units. Okay, that's a very hard question. Some profs will expect you to be able to do this on a test, some may not. Let's look at our last example. If the derivative of x is not continuous, it might be that this is incorrect. This should be the inverse derivative of y. So we find the inverse of this function, and it's now with respect to y. This might be continuous, and an example of this is vertical tangents. Then we would need to do arc length. It's going to go from C to D, square root 1 plus g prime of y squared dy. So g of y equals the inverse function of x. So c equals f of a and d equals f of b. So we have y equals x to the 1/5. So our g of y equals, we swap, and g of y equals y to the 5th. G prime of y equals 5y to the 4th. And let's just do the derivative here of y, or f. We have 1/5 x to the negative 4 over 5. And this is equivalent to 1 over 5 x to the power 4 over 5. And we see that x cannot be 0. So this is not continuous. But if we take the inverse function, we see that this is continuous because we're not dividing by 0. So we have arc length equals negative 1 to 1, square root 1 plus 5y to the 4th. Don't forget to square this. Negative 1 to 1, square root 1 plus 25y to the power of 8. I just want to illustrate that this function has a vertical tangent. And we see the vertical tangent there. Let's clear that out. Now we want to do this integral, square root 1 plus 25 x to the power of 8. We can't put y in here. The calculator only does x, so we substitute the x for y. Graph. And now we calculate this integral from negative 1 to 1. And we get an approximate value, 3.281 units. And just so that you're clear, the window for this is -2 to 2, -2 to 2. And that completes this lesson.